Hello and welcome. In this video, we're going to take a look at sets of numbers. So we'll look at natural numbers, integers, rational numbers, and real numbers. And then from there, we can take a look at set notation and interval notation, which we're going to be using a fair bit during this course. So let's take a look at the notes. And we'll start off by sort of visualizing the various different types of numbers that we might be interested in. And all of these are sort of historical. They're kind of going in order of how we invented new sets of numbers as we went along. So we'll start off with just our basic counting numbers, which would, be the 1, 2, 3, and etc. And those are called the natural numbers. Now, it's a little bit of a debate as to whether or not the natural numbers should include 0 or not. So let's say that the natural numbers include all of these whole numbers 1, 2, 3, but it's a little bit of a convention as to whether or not it includes 0 or not. Now I can kind of see both points of view as to whether or not 0 is a natural number or whether 0 is not a natural number. But I think for the purposes of this course, we're going to include 0 as a natural number because there's some other ways that we can notate the positive values. Now, if we're going in the opposite direction now, we're going to get into negative numbers. -1, -2, -3, and so on. Once we start including all of those, now we form something called the integers. So the integers include all of the negative values. And I guess I should probably include little ellipses here just so it indicates they continue going further backwards. And it includes all those negative numbers as well as 0, as well as all of the positive whole numbers. So it's a pretty big set. We've already got the integers. But that's just getting started, because we know that there's lots of numbers that go in between those values, and they can form fractions and decimals. So now we can include things like 1/2, which could be expressed as 0.5. We could have negative fractions, -3/4, or we could have decimals, 0.36, 0.725, all kinds of things. Now, at this point in time, if we start including all of these other numbers in between, we're getting into a much bigger set. And we can construct something called the rational numbers, or just the rationals for short. And rational numbers can be expressed as either a terminating decimal or a repeating decimal. And here's just a couple examples so you can see 1/2 can be represented as 0.5 with a repeating 0 afterwards, or simply just 0.5. And 2/3 can be represented as 0.6 repeating. And if you'd rather write that a different way, you can have a bar over the 6 to indicate that the 6 is repeating. Now, at this point in time, it seems like we've got all the numbers we could possibly need, but there are several other numbers that we're going to be looking at that cannot be expressed as either a terminating decimal or a repeating decimal. And that's when we look at the irrational numbers. Now, unlike before, where we were just building larger and larger sets of numbers where every natural number is an integer and every integer is a rational number, now irrational numbers don't fit into any of the previous categories. And it's not necessarily easy to understand how something like √2 is irrational. But it is something that we might have a video on later. √2 is some sort of number that's between 1 and 2, but it can't be expressed as a terminating decimal or as a repeating decimal. And another famous example is the mathematical constant I. So approximately 3.14, or if you want to continue on, you could go on forever. 3.14, and it'll just continue on. Another number that we will look at some point in time is the mathematical constant E. That is approximately 2.718. But again, that one also continues on. 2.71828, blah, 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 blah. Okay, and all of these have some significant uses. but they cannot be expressed as rational numbers. Okay, so it's time to introduce a little bit of notation. What you can do is you can start with the smallest group that we looked at, which is the natural numbers, and we'll give it a symbol. Okay, we've got n with a double bar, and this represents all of the numbers in the blue box. So this is our first concept of what a set is. It's a collection of numbers. Okay, it makes sense so far. N for natural numbers. So logically, it should be I for integers, right? Well, unfortunately, that's where the logic goes away a little bit. We use Z for integer. Now, here's my argument as to maybe why 0 should be included in the natural numbers, but it's just an opinion. We have a nice little neat notation where we can go Z, a little plus sign next to it, and that would actually indicate only the positive integers, which don't include 0. So just in my opinion, if Z plus is already a good notation to use for the positive integers, then we might as well have natural numbers include 0, so that at least we have two different things that we can use for what we specifically mean in that purpose. N includes 0, Z plus does not include 0. Okay, so now we've got two different notations. Okay, rational numbers. Now the irrational numbers we use Q, and you notice that all of these letters have a double bar on there to indicate it's a set of numbers. Now we can also indicate some sort of notation for irrational numbers, but we aren't going to be using that in particular. Really, you define an irrational number in terms of numbers that aren't rational. So it's really like the irrational numbers are numbers that aren't in Q. So it's not super useful to come up with another notation for that. But all put together, if you take the natural numbers, the integers, the rational numbers, and you take all of those rational numbers and you combine them with the irrational numbers, then we get the real number set. And the real numbers, that includes the rational and irrational numbers. Now, another definition for real numbers, rather than just thinking that it's a collection involving both rational and irrational numbers, the real numbers are basically every number that can be represented as a point on a number line. So we call this the real number line, and we can indicate places on that line including 0, which is a natural number. It's also an integer. It's also a real number. And we can include 1 on that number line if you want. 1 is a natural number. It's also an integer. It's also a rational number. Somewhere in between here, we can use fractions now if you want. We can put that 2/3 in there, and that exists on the number line as a rational number, but not an integer. And somewhere between 1 and 2, about 1.41, somewhere around here is the square root of 2. That also exists on the number line somewhere. It's between 1 and 2. And every real number can be expressed on this number line, and every point on this number line can be expressed as a real number of some kind. Okay, so let's take a look at a few of the main properties of real numbers. Okay, for the first two properties, these are properties that apply to the addition of real numbers and the multiplication of real numbers. So let's assume that we've got numbers A and B and C are any real numbers. Then they'll obey these two properties. First one is called commutative, meaning that if you add two real numbers, it doesn't matter the order in which you add them. If I add A plus B, or if I add B plus A, I get the same result. And likewise with multiplication, A times B is B times A. And I notice that we're using dots here, or at least I'm using a dot for multiplication instead of a cross, because well, crosses start to look a little bit like X's when you're doing a lot of written work. So a dot sometimes makes life a bit easier. But you can also omit the dot and just assume that AB means A times B. The associative property is if you're going to add three numbers together, then you can kind of choose how you wish to add them. If I want to add A plus B first in brackets, then I'll get a result, and then I'll take that partial result and I'll add C to it, and I get my final result. But it's just as easy, and you get just the same result if I take B plus C and add those first, and then add A to the result of B plus C. Doesn't matter. You get the same thing. And same for multiplication. Now there's one other property, and it involves both addition and multiplication together, and this is the one that can cause a lot of mistakes if you don't do it properly. This third property is called the distributive property, and it can be distributing from left or distributing from right. And so it involves both multiplication and addition. You see, we've got addition in brackets, b plus c, and if you take that and multiply it by a on either side, then you would take that a and you multiply it onto b, you take that a and you multiply it onto c, and then you add those two results. But the multiplication would be the first operation you would do after you've expanded out, once you've distributed. So going from what we have on the left-hand side, going to the right-hand side, we call this expanding, or distributing. You're distributing the a, but you can also see it's expanding. It looks a little bit less compact. Going the other direction, if you wanted to see something get more compact and maybe more neat to write, a times b plus a times c can be changed into an equivalent form, which is just a times bracket b plus c. Going the opposite direction, we call this factoring. Okay, so that would apply to any three real numbers a, b, and c, but you got to be careful about the order in which multiplication and addition are handled. All right, let's take a look a little bit more specifically about some of the typical operations on rationals. Now, rationals can be expressed as a decimal or a repeating decimal, but oftentimes it's a little bit more useful to write them as a fraction. And, well, if you haven't had to add and multiply fractions for a little while, it's probably good to go and review that. Okay, so this only applies to Q, the rational numbers. Because if you have an integer, you don't have to write it as a fraction. And keep in mind that you can take a fraction and then convert it to a decimal, but a lot of times you'll be more at risk of losing accuracy. So it's better to keep things as a fraction. All right, so first operation, and probably the easiest one, is let's take two fractions and we will multiply them. So we'll take something like a over b, and we're going to multiply that by c over d. And these are two fractions, and we're going to assume that b does not equal 0. We're going to assume that d does not equal. Okay, how do you multiply fractions? This is a much easier operation than you might think, even though multiplication is oftentimes something you learn after addition. In this case, it's actually a lot easier. You just multiply right across the top, take a times c, and take b times d, and make sure you keep top on the top, bottom on the bottom. And at this point in time, let's not call it top and bottom. Let's kind of make sure you know the correct terms here. All of this is on the top is called the numerator. And so you multiply the numerators, and we multiply denominators. Okay, our next operation we'll look at is division. So like before, I'm using the division symbol here, which actually may not be, you may not have thought about this, but the division symbol is basically a fraction. You can see how division is really just a bar with a thing on the top and bottom, because division is much like a fraction. The fraction a over b is, you can just think of that as like a divided by b. So that's how the division symbol looks the way it does, really. Now this is a little bit more difficult. You just got to remember one thing, is that a over b divided by c over d is actually the same thing as taking a over b and multiplying by the reciprocal, b over c. Okay? Now in this case, we'd have to keep in mind, we can't let b or d be 0, because otherwise these fractions don't make sense. But also c cannot be 0. Otherwise we'd be taking d and dividing it by 0, and we can't divide by 0. All right, so this is called the reciprocal. We take c over d and we flip it, and then we can just apply normal multiplication rules after that. Okay, well, now we get into a little bit trickier. Addition or subtraction, they're more or less the same. It's easy to add fractions once you actually have a common denominator. A over c plus b over c is just adding numerators together. And you have a common denominator. Okay, that's all great. If you ever wanted to take 1/4 and add 3/4 to it, you'd have no problem. If you want to add 1/5 and 3/5, you'd have no problem. But the moment that you don't have the same denominators in each fraction, then you're going to have to do a little manipulating of individual fractions in order to get a common denominator. So now the next operation on here is how do you take a fraction and give it an equivalent form so that you can change the denominator to something else. Okay, a over b is just a single fraction. If you wanted to get an equivalent fraction, then what you can do is you can take a and c and multiply top and bottom by some sort of factor, as long as that factor is not 0. Because then you'd end up with 0 over 0, which is undefined. But you can take 3/4, and if you multiply top and bottom by 2, you'd get an equivalent fraction. 3/4 is the same thing as 6/8. And this can be worked out in both directions. If you have 6/8 and there's a common factor on the top and bottom of 2, then you can cancel them out. So you can either get an equivalent fraction by multiplying top and bottom by a common factor, or if you find a common factor top and bottom, you can cancel it to get an equivalent fraction. Now, a common mistake here is that you cannot cancel common terms if you have addition or subtraction on the numerator and denominator. So just a little side note here as a common mistake, that you cannot add a value to the top and bottom and say that is equal to a over b. That doesn't work, not in general, okay? So don't try adding a common term to the top and bottom, and please don't try canceling a common term on the top and bottom. Now, one other main property here, and this is also a way for you to check and see whether or not two fractions are equivalent. Let's suppose that a over b is equivalent to c over d. So we call these things equivalent fractions. Suppose we could call them equal fractions, but they aren't expressed the same way, so equivalent might be the better term here. If two fractions are equivalent, then this whole equation can actually be expressed equivalently as a times d must equal b times c. And we call that cross multiplying. So as an example of cross multiplying, you can see that we talked about 3/4, and if you take that and you multiply top and bottom by 2 each, then you would end up with 6/8. Now we know that those are equivalent fractions from that fourth property I was just talking about, but you can also check it by cross multiplying. 3 times 8 is 4 times 6, and both sides equal 24. Now, if you try to cross multiply and the two sides are not equal, then you must not have had equivalent fractions. Okay, so we've talked about a few different sets of numbers: natural numbers, integers, rational numbers, irrational numbers, and finally the real numbers. Now, each of those are sets of numbers. And then we can take sets and we can narrow them down into smaller subsets if we want to give a different notation. And then we can also represent sets in terms of intervals. So we'll take a look at that. A set is a fairly basic concept to understand. A set is nothing more than just a collection of items. Rather than calling them items, though, we call those items elements of the set. So we've already taken a look at natural numbers, integers, rational numbers, real numbers, and these are all sets. The elements of those sets are numbers, but we could also have a set of trees if you wanted, where you'd have oak and spruce and pine and birch, and then we could make a collection of trees, and those trees would be elements of the set. If you want to say that something is an element of a set, that's a lot of words, and being, a math guy, we try to trim down the number of words we're using and put some notation to it. So we have this sort of weird looking E. It's kind of curved and it's a little bit smaller than a normal E might be looking. That there means is an element of. So with some examples we've already done, you know that -3 is an integer And we can cross that out if it's not an element of something. -3 is not an element of the natural numbers. √2 is not an element of the rational numbers, but √2 is an element of the real numbers, for example. And if you want to just have a very small collection of numbers, we can actually just list them out. Suppose you want to create your own list and you don't want it to be the natural numbers because that's really big. Maybe you only know 4 numbers. So what if we just want to include your favorite 4 numbers in a new set? Since I'm going to be calling this my set, this is Steve's set, I'm going to call it S. And S is equal to whatever I want to include in there. But we can't just have a list of my favorite numbers, 2, 3, and 5, for instance. I need to enclose those in curly brackets. And that's the particular type of bracket that we use for sets. You may call them braces instead of curly brackets if you like. Another way you could define your own set is if you wanted to, you could kind of use a little bit of a description, and we call this set builder notation. In set builder notation, you can define your own set. Maybe we'll call it P. And again, we use curly braces. And what you do is you just form a template. It's like a little cookie cutter. This is going to consist of any arbitrary value x. Now, I got to tell you what x is. I'm going to give a description of x. After that, we put a little bar. So already you know that this is sets of individual numbers. X is an individual number. And I'm going to say that x is a prime number. And that should be enough of a description so that you can start to form values that are included in that set. Prime numbers are numbers with the factors only being 1 and itself. So 2, 3, and 5. They're already in S, but now I'm also including 7. And I'm including 11 and 13 and all the other prime numbers. There is one particular set that might not seem like it's super useful, but we can actually define a set to have nothing in it. And it looks a little bit boring. You could just write it as 2 curly braces with just nothing in there. That is a set. It's a set of nothing. And it's called the empty set. And that's going to be a big O with a cross through it. That's the empty set. So it shouldn't be, you shouldn't use a 0 with a cross through it when you just mean 0, because an O with a cross through it does mean something other than just the number 0. An O with a cross through it is actually a set with nothing in it. Okay, now sets, you can either have big sets that we've just looked at, natural, integers, rational, and real, or it could just have a few sparse elements if you just want to list them out. But if you want a continuous set of numbers along the real number line, and it sort of has a start and an end point on a line segment, then we can use something called interval notation. Interval notation is just a different way to describe a set, or at least like a different notation to describe a set, but it's only going to be used for a continuous segment of numbers on the real number line. Here's my real number line. I've put 0 on there just because it's nice to sometimes know sort of where the origin is for all of the natural numbers, but it may not be a number that I'm interested in. Let's suppose I'm more interested in all of the numbers starting from 1 and going up to 5. So what I could do is I could kind of shade that in, and you'd see that every number here is being included from 1 to 5. And because this is just a continuous line segment, there's infinitely many real numbers that can be between 1 and 5. So it's a little bit harder to list them out. And it's only a subset of R, so we can't just say that this set is R. What we do is we use square brackets and round parentheses. And we indicate the endpoints of this line. So the endpoints here are 1 and 5. And we put those in brackets. So 1, 5 is our interval, and then we can either use square brackets or we could use round brackets. Now, square brackets include the endpoints, and if you'd rather use round brackets, it means just almost the same thing, but does not include 1 and 5. It really depends on what you mean to use in the given circumstances. And so when we're putting a line segment on the real number line, it's also good to include some sort of notation, whether it includes the 1 and the 5. We would have to use a filled in dot from 1 to 5 to include the endpoints. And if we use a hollow circle, that does not include the endpoints. And you can use combinations of these two things. You can have a square bracket on a 1, and you can have a round bracket on a 5. In this case, that would be including the 1, but not including the 5. And last combination here, a round bracket on the 1 and a square bracket on the 5. If you don't want to include the 1, you do want to include the 5. Now, in that last example, 5 is included, and so is 1.00001. And so is 1.0000001. You can get really close to 1, but 1 itself is not included. Now, what if you wanted to perhaps have multiple line segments and combine them together to form one set of numbers? So it wouldn't be a continuous line, but you'd have separate lines with breaks in between them. Then what we can do is we can use an operation on sets that is used to combine sets or merge sets in some sort of way. And there's two different operations that we're going to look at on sets as to how we might want to merge things together. Okay, I've got two sets here, A and B. A is from -2 to 5, not including 5, and B is from 2 to 8, but excluding 8. Now, I have a couple different options as to how I might want to combine those together. Perhaps I want to include everything from the blue line and everything from the red line. Well, there are some numbers from 2 to 5 that I don't need to count twice. So it's not just A plus B. We have a different notation for that. So the first thing is called the union of two sets. And if we wanted to form A union B, then we put an operation between the two of them, which is a cup. It kind of looks like a U. This would be including everything in both the blue and red intervals. So you can see that -2 is included, so that's going to be a solid dot. And it includes everything up to 5. But 5 is not included. However, the red line takes care of 5 because it includes everything from 2 all the way up to 8. However, it doesn't include 8. So that's going to be a round circle, and as a result, it includes everything from -2 to 8, but not including 8. As a result, A union B is the interval from -2 with a square bracket to 8 with a round bracket. Now here's another thing we could do with two sets, A and B, is perhaps you actually only wanted the numbers that are both shaded in blue and shaded in red. Not the numbers that could be in blue or red, but the numbers that are in blue and red. Well, in that case, we call that the intersection. Now, the intersection has more or less the same symbol, just flipped upside down. So this is going to be a cap. We say that union is a cup and intersection is a cap. So it's like an upside down U in a way. Now, if you think about numbers that are shaded in blue and red, you can see that every number that's between 2 and 5 would be included. So we know that's going to be shaded in, no problem. But what about the endpoints? 5 is not a number that is actually shaded in blue. It's not included in the set A. So since it's not blue, it's definitely not in the blue and red zone, so it can't be included, and that would have a round circle. But +2 is included in both the blue and red set, so that's going to be having a shaded dot. And this set would consist of everything in between. And so as a result, A intersection B is a interval from 2 to 5 with a square bracket on a 2 and a round bracket on the 5. Okay, well that just about sums up everything that we need to know currently for sets of numbers and interval notation. So we're going to be taking that forward and looking at other properties about specific types of operations on numbers, and then we'll be eventually using all of this when we get into functions. So those are all for future videos, and I hope I'll see you again later.